Mr. Richens here with another lesson in physics. Today we're starting Unit 2, Measurement and Mathematics. Our first lesson is going to be about data and measurement. I'd like to start with a clip by William Thomson, Lord Kelvin. He wrote, "I often say when you can measure what you are speaking about and can express it with numbers, you know something about it. But when you cannot measure it, cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginnings of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be. So therefore, if science is measurement, then without metrology there can be no science." Physics has always been closely tied to measurement and mathematics. In fact, it was perhaps the first discipline to make extensive use of measurements and mathematical relationships between those measurements. Chemistry and biology and other disciplines have expanded in their use of measurement and mathematics, but it began with physics. In physics, we encounter two types of data. The first type is qualitative data. This is data that describes an object, a property, using adjectives like red or large. It can sometimes be quantified, like using numbers to substitute for the adjectives. The other type of data is quantitative data. This is data that's specified using numbers. Most often, it's the numbers that are derived either by counting or by measuring. There are two types of quantitative data. Exact numbers, also known as discrete data. These are arrived at by counting or by definition or convention, like when we say there are 100 centimeters in a meter or 12 inches in a foot. The second type, measurements, are continuous data. These are an estimation of an actual quantity and arrived at by using an instrument. Measurements are approximations of true but unknown values. The act of measuring involves some estimation. The divisions on a graduated scale have gaps between them, and we need to estimate where our value falls between those two gaps. And for that reason, they're always approximate. Measurements have three parts. They always have 0 or more certain digits, ones that we know with accuracy. We know because the graduations on the measuring instrument tell us that they are true, that the value we're measuring is above one graduation and beneath the next graduation. The second thing that they all have in common is that they have one and only one estimated digit. What it is between those gaps between the two graduations, something that we can only guess at really, looking where it is relatively between the lower value and the higher value. The third is units. Units are necessary in order to give sense to the measurement so that we know whether we're talking about 3 minutes or 3 miles or 3 kilometers or 3 days. Standard units upon which a measuring system is based need to have certain characteristics. They should be well defined. That definition needs to be known by everyone. They need to be of suitable size, not too large or too small. They need to be easily reproducible so that researchers all over the world can have access to them. They also need to be uniform. We can't have them changing from day to day or from place to place. They have to remain the same so that we have confidence in our measurements. In physics, we'll be using standard units, part of the International System of Units, the SI. There are actually six standards. We'll be using 3 initially. They include, for mass, the kilogram, for dimension or length, the meter, and finally for time, the second. In addition to standard units, we have derived units. These are based upon the standard units and come about through the application of formulas to measurements. For example, we have for volume, there is no standard unit of volume, so we use the cubic meter, which is made by multiplying together 3 measurements of length. We also have the unit of force, which is derived from a kilogram, meter, and seconds squared. It's called a Newton, and you'll be using it a lot later in the course. In addition to units, the SI has a series of prefixes. They allow standard units to be scaled to larger or smaller units by orders of magnitude. Common prefixes include milli, meaning 1,000th, as in there are a millimeter is 1,000th of a meter, or centimeter, meaning 100th of a meter. Finally, kilo. There are 1,000 meters in a kilometer. In addition to prefixes, we have the advantage of scientific notation. Scientific notation allows us to use powers of 10 to represent very large or very small numbers. For example, the number of molecules of water in 18 grams of water is 6022 followed by 20 zeros. I can't even name that number. But we can express it without all those zeros by using scientific notation. And so we can write it as 6.0222 times 10 to the 23rd, which is much more convenient. And we don't have a metric prefix that would apply to that. Since measurement involves approximation, estimation, there are two types of errors that we can encounter. The first type is systematic error. Systematic error is often caused by operator error, miscalibration of instruments, or poor experimental design. Systematic error is avoidable by properly training our operators, calibrating our instruments, and designing proper experiments. In addition to systematic error, random error is present. This is unavoidable. Every time we make an estimate, it's going to be too high above or too far below the actual value. We can't eliminate random error. Accuracy and precision are two terms that were used to describe measurements. Accuracy refers to how close our estimate, our measurement, is to the actual value we're trying to measure, while precision is how close repeated measures of the same quantity are to each other. It's a measure of our ability to reproduce our measurements, that we do it consistently. For example, imagine an archer shooting arrows at a target. Our first archer places arrows all over the target. There's no cluster, they're not close to the bullseye. We would say that this archer had low precision. His arrows weren't clustered together. Also, he had low accuracy because the arrows weren't close to the bullseye. Generally, this is the result of systematic error and random error working together. Our second archer fires a group of arrows, and they land very close together, but they're quite far from the bullseye. This repeatability represents high precision, or exhibits high precision, but it's low accuracy because it's very far from the bullseye. This is also the result of systematic and random error, often a miscalibration of an instrument, allowing the measures to be closely gathered together, but away from the true value. Our next archer fires another set of 4 arrows. These are close to the bullseye, but they're kind of spread out. This would represent a low precision because they're not tightly clustered together, but it does represent high accuracy, particularly since we can take the average of the 4 arrows and come close to the actual value that we're looking for. This is typically the result of random error. Our last archer fires their 4 arrows. All of them hit the bullseye very close to each other. This represents both high precision and high accuracy. This is desirable, but often this type of accuracy and precision can be suspicious. It's as if the data were made up to fit a certain model. There's always going to be some error in an experiment. We want to minimize it as much as possible, but we can't eliminate it completely. So how do we deal with it? One way is to make sure that we use our instruments properly and that we have proper experimental design. Random error can be minimized by collecting large amounts of data and applying a statistical method. Most often averaging the data will work. That's all for lesson 1. I'll see you again soon.